this is RC Jim, and here we got another helpful video for you on some tips and tricks. In particular, what we're looking at today is selecting the proper set of components for an electric radio control plane. Now, when you buy something like one of the guys up there that is already set up with electric motor and ESC, and it's basically a bind and fly, ready to go set of airplane, it's pretty simple. They've already selected the prop, they selected the ESC, they selected the motor, and so basically all that's left for you to do is to get the battery, and of course you'll get one that they recommend. But if you are working on something where, say, you're converting an old nitro plane into electric, or perhaps you're purchasing a almost ready to fly aircraft that doesn't have the components in it yet, or perhaps building a balsa model. In any of those, while there will be some recommendations given, the recommendations might not exactly suit what you really want. Each of us have seen videos even about ready to fly airplanes, or bind and fly airplanes, where they do the test flight and they say, oh, I'd really like to have a little bit more power, a little bit more this or that. Or perhaps even like with prop selection, you're at the field and you break a prop and you don't have the exact same thing and you wonder, oh, can I get by with using this one? Yeah, there's a lot of things that you really need to understand to keep yourself out of trouble. And as we pointed out in previous videos, while electric motors are handy and nice, there are certain dangers that we need to be aware of. And many of those dangers can be avoided by selecting the proper set of components. So, dangers of fire, heat damage, and explosion can greatly be reduced by ensuring that your system is not going to draw more amperage than what the components are rated for. So here are some helpful steps to allow you to be able to work that out. Now, you need to begin with a motor selection. And motor selection is more than just picking something that fits in the spot and looks nice and whatever. There's a lot of things to consider about that. Now, when I was first getting ready to convert this old Great Plains Trainer 40 to electric, as an engineer, I thought the matter would be quite simple. Just match the horsepower. And doesn't that make sense? Same power, ought to give you the same set of results, shouldn't it? And so I looked up with regard to my good old OS Max FX46, beautiful motor that works really great. And that, according to the manufacturer, has 1.65 horsepower. Well, you can convert horsepower into watts by multiplying by 746. And so you multiply that out. And what did I get? We end up with the watt output of being 1,231 watts. Of course, that's the output. Anytime you're measuring horsepower, what's it puts out. It's not the energy value of the fuel that you put in. And any motor, whether it's a nitro or an electric motor, has got a level of efficiency that's probably a lot less than what you might think it ought to be. Essentially, heat is being created that does nothing but, harm components and warm the atmosphere. All of that heat is energy, and that's being lost. Okay? And of course, you got all kinds of other things that come into it as well. But anyway, as you think about that output, okay, we have to match that with an electric motor. And so I figured that, well, okay, if we've got the equivalent of 1,230 watts output, then I need to match that as far as an electric motor is concerned. And so I had a look through there, and I found that essentially it was telling me that I needed to pick much bigger electric motors than what the manufacturers were recommending. When I looked up a motor that was recommended to replace it at 46, it would be a lot less wattage than that. And so it seemed a little bit strange to think about that. Okay, so the power that's going into an electric motor is going to be much greater than the actual power that it delivers to the prop. And as I've done a bit of research on this and had a look at people that have tested them, they reckon that around a 60 to 80% efficiency would be common. So if we work on a 70% efficiency, then even taking a OS Max 40 with 1.35 horsepower, we end up requiring 1,438 watts or 1.4 kilowatts input into the electric motor. But as we think about a Dualsky, in these charts here, Dualsky, this 4255 is recommended for a 46 to 55 two-stroke. So that's the 46 is at the bottom end of that, so certainly you'd think that'd be plenty big. And yet, as you look at that, its peak power is 1,128 watts. And that peak power is just what it can deliver for 15 seconds. And then you got to back off. You know, the nitro motor, it can run all day long, you know, at full throttle. And so I was just really puzzled by this as to why there was such a big difference between the two. And questioned whether it was really valid what the manufacturers were telling us about the electric motors. As we have a look at what would be required, if you looked at just simply the horsepower, we would actually be into a Dualsky 5050. Now, I'm not sure if you're familiar or not with the basic conventions on motor sizes. But as you look at pretty well any electric motor, it'll have a 4-digit number as the main part of the number. And the first 2 digits of that are basically going to be the diameter of the motor. Now, usually it's going to be the diameter of the rotor, and in a few cases it'll be the diameter of the case, but you know, essentially it's how big around it is. The second 2 digits are going to be how long the windings are from front to back. And again, there can be some variations as to exactly what they're measuring, but essentially you're thinking of diameter and length. So as you go bigger, bigger diameter, bigger length, you'd expect to get more power out of it. So with this Dualsky XM5050, as we think about the power on this, we get up to a peak power of 1354, which at least for a short period of time is up there in the range that we see the power of the OS Max 46 being able to develop, or the 40, I guess. But we note here that they're saying that it's equivalent to a 55 to a 65 nitro motor. And so that is really strange. So as I thought about this, I thought, well, tell you what, let's look into this a little bit deeper and let's take a different approach to it. Comparing horsepower is great, but really at the end of the day, what makes the airplane go is thrust. And so if we can compare thrust between these, that will really do a lot. And in actual fact, thrust is actually a lot easier to measure as well. You know, you hook up to your airplane to a set of scales and crank up the throttle, and it'll tell you what the thrust is, you know. So it's something that we can research and find for the glow fuel motors, and it's something that we can look up for the electric motors, and then later on we'll do some testing to actually test it out in real life. Going back to the OS Max 46, I did some research online, and I found a fellow that reported on his particular plane and the testing that he did on it. And he said that his OS Max 46 was developing 3,261 grams of thrust. So the thrust, 3,261 grams. Now, that was with a master air screw 11x7 prop, and he clocked it at 12,300 RPM. And again, that's something that's just an ordinary person can check very easily with an optical tachometer. Okay, so that gives us something to work with. And by the way, for all of this research and things like that, as you look in the description down below, I'll be putting links in there for each of these that you can look up. And eventually I'll have this all written up on my website so that you can come back and refer to it, because I realize there is an awful lot of information here, and just listening to it once, you know, you're probably going to miss some of it. But we'll go through the explanation anyway, and you can look up the details later. Okay, if we want to duplicate that, the nice thing about Cobra motors is they give you actual test data. So I've gotten this off of the internet, and it's accessible to any of you, and again the link is down in the bottom below. And this is just a small piece of the chart. You know, each one of these charts, they list heaps and heaps of props, you know. So I've just given you a set of APC and master props here that are in the range of what we're looking at. But as we look through here, and basically I looked through a number of motors, and I was looking for one that would give us thrust in that area. So that you got the column here that's got the thrust. And I saw that if we got one of these 4130 motors, that it should generate 33,776 grams of thrust with a 14x7E prop. Okay, so 3,776 grams of thrust. And so that's going to be very, well, a little bit more than the thrust that you would get on the OS Max 46, the 3776. Okay. It was interesting that as I also then considered about the Dualsky, and especially the one that is considered to be the equivalent for the 46, that they recommend that the maximum weight of a sport model is 3.1 kilos. Typically, a recommendation for a sport model is going to be that the thrust equals the weight of the model. So I'm expecting that they reckon that 3,100 grams of thrust is going to be generated by that. And I've also looked up on another site on the internet where they give theoretical thrust based on various props spinning at given RPMs, and working out with the kV value of the RPM, I come up around about 3,000 grams of thrust for that particular motor. So that one is just a little bit less than the thrust that the OS Max is developing, and with this other selection here we got a little bit more. So that all seemed to be pretty good. But as you look at that, it's interesting that you look at the watts input for the 3776, it's only 877 watts. We were thinking it would have to be something like, well, 1400 for even the 40 motor, you know. And so that's a huge discrepancy as you think about those two. So it's really strange. But with Cobra here, they've given us actual test data where they've actually put the prop on the motor and spun it up and measured the thrust that it's generating. So I think we can say that it's reasonably accurate to say that it's going to develop that amount of thrust with just that amount of watts. Now, one thing to be very careful with regard to any of these sort of comparisons that you're doing is to make sure that you're comparing apples with apples. So as I think about the OS Max 46, I realize that this thrust that it's developing, it could do that all day long. The entire flight, you could run it at full throttle and you're going to be okay. Okay. But as you look at something like the Dualsky, as they specify the watts, notice it's the peak power of watts, 15 seconds. So 1128 watts it can only handle for 15 seconds. That's a lot different than the Cobra, where the Cobra is capable of, what is about 80 amps or something like that as the peak. And we're figuring 60 amps as a safe sort of thing to use over a longer period of time. And so all of this, with the green ones, they're all within that range to where they're falling under the 60 amps, as you see the column here. And in this particular one that we selected here, it's only drawing 40 amps. Okay. So that's a continuous sort of thing. So as we do the comparison on my little comparison chart over here, as I've worked out some things that they don't tell us, I've worked out, well, they do tell us it's 621. The cruising power is 621 as compared to the 1100 or whatever it is, 1128. So we've got that in there, and that's comparing similar watts with the other ones. Now, just thinking a little bit more about this chart, I mentioned about the colors on it. The green is saying that it's running reasonably efficiently, and it's within the limits of the amperage that the motor can handle. When you get into the yellow, it's saying that, okay, it's running very efficiently, but you need to be careful with regard to the use of full power, that you need to limit the use of full power to short bursts and things like that. And then in the red, it's saying, hey, whoa, it's no good. That's going to draw too much current. Essentially, as we've mentioned before, with regard to electric motors, with the brushless DC motors, they are going to draw whatever current they want from that battery, and the battery can deliver the current, but the systems can't handle the level of current. They get hot and they melt and cause all kinds of problems. So that red is saying that area there. And then the blue is just simply saying it's not efficient at that level, So we're looking for something in the green. You could get by with something in the yellow, but you would have to make sure that you're not really hammering the thing constantly with regard to the throttle. So I asked myself the question then, why is it that a nitro motor needs to have more horsepower in order to generate the same amount of thrust? It doesn't make sense. I mean, power is power, isn't it? Well, as we think about the power, there can be a whole bunch of factors that affect performance. Now, one thing is the prop diameter, the diameter of the outside of the circle of the prop. If it's a two-bladed prop, the total length of the prop. Bigger props, ones with longer blades on them, are going to be more efficient than shorter props. Okay, that's just a very basic nature of the prop. Furthermore, some of the electric props are going to be more efficient than the nitro type props. They're going to be a little bit easier to spin, and the aerodynamics of it are going to be a little bit more efficient with regard to that. Another thing might be that the nitro motor manufacturer may be testing their motor in very ideal conditions, perfect tuning, magic fuel, although usually they'll specify the percentage of nitro at least when they talk about their test data. But they might be a little bit optimistic. Manufacturers like to be that way. And that might also be true with regard to specifying the equivalent for the electric motors. They might be thinking, yeah, it's roughly equivalent as long as you don't stay full throttle too long, and most of us don't, but they might be taking that into account as compared to, saying, set up a race plane or something that is going to be going flat out for a long period of time. And who knows, there might be other factors as well. But again, the bottom line is we need to generate the thrust, and that will be determined quite easily. Now, I'm not going to get into it today, but there is another factor with regard to comparing the various props, in that as we look at the props that are recommended for the different selections here, we got an 11 by 7, 14.4, 14.7, and a 10.7. With a higher pitch, and the pitch has to do with, as it spirals through the air, how far is the plane going to go forward in one revolution of the prop if there was no losses, if it's going through butter or something like that, to where, it goes the full distance that it ought to. But with those higher pitches, they're going to tend to perform better at speed. The lower pitches will tend to be better out of the hole, getting started. So if you're testing the thrust of the plane sitting on the bench, the thing is not at speed, and so in general the lower pitch props are going to appear to be better than the higher pitch props. whereas the higher pitch props will tend to pick things up when it gets up at speed. So that's something to consider. And if you're doing a lot of aerobatics where you do tumble turns and various things like that, and you need to get going from 0 airspeed to something else very quickly, then you'll tend to use a lower pitch prop for something like that. Okay, but the other thing that we consider here is when we look at the prop size, an 11 by 7 compared to a 14 by 4, that 14-inch prop, that's huge. And if the plane was designed to operate with an 11-inch prop, you may not have enough ground clearance. I mean, right there, that's what is that, a 15-inch prop. Okay, and so that's just an inch longer than what we're talking about here. I don't happen to have a 14-inch right handy. But that's an 11-inch prop. Okay, so have a look at the difference between those two. And you're talking about a huge difference, and you might be, doing a little bit of rototilling the ground if you have too much of a big prop. So I thought, well, okay, let's have a look at a solution where we can use the electric motor with something that's no bigger than 11 inches. So the first thing I did is I said, okay, the C4130, we've got a kV value of 450 RPM per volt. So if I want to go with a smaller prop, I'm going to have to spin it faster. And so I had a look at the highest kV value that you could get in that motor size, and it didn't generate enough thrust. So it still was no good and not enough thrust with an 11-inch prop. Okay, so I thought, well, okay, let's go the other direction. Let's go to a smaller motor that has a higher kV rating. Because in general, you will find that smaller motors will tend to have higher kV ratings, and the great big motors will tend to have lower ones, because the great big ones are swinging great big props. They don't need to spin them so fast because the thing is so big, but the smaller ones, they can really wind it up. So I went down a size. I went from the 4130 down to a 4120. So 41, that's saying that the case diameter is the same, but instead of being 30 millimeters long, it's 20 millimeters long. Okay, so a significant smaller motor. And with that, I could go up to 850 kV value. So with the 850 kV value, I found that there was a couple of solutions there. First off, in the yellow, we got an 11 by 5.5E that would generate 3,776 grams of thrust. So that's very good, and turning 12,760 RPM. And so you think about a comparison up here, the nitro motor, 12,300 RPM, 3,261 grams of thrust. And with this one over here, we're talking about a little bit more thrust, a little bit more RPM. Certainly the same sort of class of operation in terms of RPM and what the thing can generate and all of that. And actually that's with the three-bladed prop, because I saw that this one was in the yellow, and I thought, well, okay, that's not really fair, because that means I have to, back off a little bit. Let's pick one that's in the green. And so if I went to a three-bladed prop, I could go down to a 10-inch prop, a 10 by 7 by 3. It's still going to generate 3,741 grams of thrust, and it's going to turn 12,476 RPM. Now we do note that with the bigger motor up here, we're using a 6S battery, 22.2 volts, and with the smaller motor, we're using a 5S battery with 18.5 volts. Now you might think immediately that that means that this battery is going to be smaller, but note that this one has got to deliver around about 60 amps, 59.73 amps, whereas this one has only got to deliver about 40 amps. That means that if you're going to have the same length of flight, we need to have a larger amp hour battery for this one. So even though it's got one cell, it needs to have a higher capacity, and so it ends up the batteries being very similar between the two, just this motor being a bit bigger and heavier than that one. Now, all of this began with a comparison with a nitro engine and just simply trying to get an equivalent. But if you're trying to set this up for a particular plane, you also want to think about your thrust to weight ratio. Now, we mentioned for a sport plane, about 1:1 is suitable. So if we are developing 3,700 grams of thrust, then that means the plane with everything in it, battery and all, could weigh about 3,700 grams, 3.7 kilos, and that should perform very nicely. If you're into 3D flying or something like that, then you want a lot more. I suppose ideally you'd like about double. You want the thing to be able to accelerate going straight up, you know. So in that case, you would take half of that for the weight of your plane, and so you'd have whatever that is, 18 or so, 1.8 kilos for your plane if it's a 3D model. So that brings us then to the ESC selection, electronic speed control. Of course, that's what is going to determine what the motor gets in terms of the power going around the windings to make the motor spin, telling it how fast to go. And it needs to be something that can handle the sort of current that's going to be developed by the motor. So what we do is we start out by having a look at the specifications for the motor itself. And for this Cobra 4120, it says that the maximum continuous current that it can handle is 75 amps. Okay, so even though our motor is only expected to generate, what do we got here, 60 amps, we want to be able to handle the 75 amps with the ESC. Why is that important? Well, the 60 amps over here will vary depending on what sort of prop you put on it. And you may decide to change props later on. So you want to make sure that the ESC can handle whatever the motor can handle, and then as long as you select a prop that's going to be suited for the motor, then the ESC is going to be fine. So we need 75 amps. Generally, I like to stick with the same brand as the motor for the ESC, just making sure they're all compatible. It's kind of like when you have work done around the house and you got a contractor coming in, and you know, if you have a different supplier than the provider or whatever, you know, whatever goes wrong is always the other guy's fault and nobody takes responsibility for it. Well, yeah, if you stick with the same manufacturer, you know that the things ought to be compatible. So with Cobra, they've got an 80 amp ESC, so that has a little bit of headroom that's extra there, so that's very good. And so that would be the ESC to select. We checked that it's good for 2 to 6 cells, so we're using a 5-cell situation over there. So we've got capacity there. Of course, the voltage is related to the number of cells, so that's fine. Can handle a burst current of 100 amps, so we don't expect to do that, so that's all fine. Then it tells us the dimensions and all of that kind of thing. So that's our ESC, and that's going to do the job for what we need. But there are some things that you might want to also keep in mind when you select the ESC. For one thing, with Cobra, they don't have any lesser options. It comes with this, but you want a switching type of battery elimination circuit. The battery elimination circuit is what provides the power to your transmitter, or sorry, the receiver, power to the receiver, which in turn is providing power to all your servos and things such as that. And it allows you to use the single battery to both power the motor as well as power the electronics in the plane. And a switching type of BEC is going to be more efficient than one that just simply puts resistance into the circuit to bring the voltage down, and you end up creating both heat and using power to do that. So you want a switching BEC, and most of the decent brands and stuff like that will do that. There are ones that provide different ranges of voltage for the BEC, but that's really not going to be an issue for you. Again, we're going to have a further video that goes into more details on these things with regard to the programming, where you can select different voltages and things like that. but you'll find that your receiver can handle a wide range of voltages, and pretty well all of the ESCs are going to give an acceptable voltage for that. There's one other matter that I found rather confusing, and that's called active freewheeling. Now, you get confused easily because there's at least one manufacturer that I found that refers to the prop freewheeling as being the brake is off, okay? But active freewheeling is not talking about the brake on the prop. It's actually talking about the electricity inside the motor. And so with the motor, the ESC is constantly providing power to two of the three windings, and of course it could be multiples of those going around, but two at a time going around the whole thing. But it's constantly switching it on and off. And it does a lot more of that switching on and off when you're at partial power, because it's actually a whole bunch of little pulses of power all together to reduce the power as compared to one long surge of power for each sort of cycle that the thing goes through. And in order to keep the thing from sparking and creating abnormal voltages that could really cause damage to the motor, they have to dump that power each time it's turned off. And with a older style, and I say older, is still a number of them still have this, the lesser sort of style, however you want to call it, it uses a diode to do that, and the diode will put resistance into the circuit, and it's going to create heat. And so partial power, you're going to be using additional power going through that diode, and it's going to heat up the motor a little bit more. Whereas with a active freewheeling ESC, it's going to use another transistor in that place to dump that power, and it doesn't have anywhere near the same sort of resistance, and it doesn't create the heat, and it doesn't use that extra power. So they call that active freewheeling, and again we'll have another video that we get into that. But just to note at this stage, the Spectrum Avian, the Hobbywing, Funfly, and Turnigy V3 are three of the brands and models that have active freewheeling. There are some other ones that aren't so familiar with me, but anyway, that'll just help you with regard to that. And as far as I know, the Cobra doesn't have the active freewheeling. Having said that about the active freewheeling, as I read various chat groups and things like that on the internet, and the people are discussing the benefits of it and all, they don't seem to think it's a huge big deal. As far as the heat goes, it's happening when you're at partial throttles. The heat isn't that big of an issue at that time, and the amount of power that's lost by the current going through that diode, it doesn't seem to make a huge difference on the flight times, but obviously any benefit would be a good benefit. Okay, now what about the battery? Okay, naturally we're with our radio-controlled airplanes, we're using Lipo batteries, lithium polymer, when we worked out what we needed in terms of a motor, it recommended a 5S battery. Of course, with any motor, you could always go to a lower number of cells, but then having less voltage and less performance out of it. So we want a 5-cell battery, and at 3.7 volts per cell, that gives us that 18.5 volts that they're requiring. But we also need something that's going to give us the flight time that we need. And that's something that we can calculate. Let's say we want to, first off, fly at, say, half throttle on the average. So we can do 60 amps full throttle. Half throttle would be 30 amps. So we start out saying, okay, we got 30 amps. Now, what time do we want to fly for? How long? Well, let's say 7 minutes. So you got 7 minutes divided by 60 minutes per hour. So that gives us hours. So a fraction of an hour times 30 amps, amp hours. Okay, we got that. So to get milliamp hours, going to multiply that by 1,000. And then we don't want to completely drain the battery during that period of time. We would like to end with, say, 30% capacity at the end. That both allows us to be able to store the battery partially charged, which is what we want to do. Also gives us a safety factor, because we're saying we're going to fly at half power on the average, but what if we're pushing a little bit harder? If we end up drawing 45 amps, let's say, that's a huge difference, and we could drain the battery. So we want a safety factor. And if we want to end up with 30% charge in the battery, then we got a 0.7 safety factor. That's to say this power here is 0.7 of the total. And so we're going to take all of that and we're going to divide it by 0.7. Now, if you multiply that out, what does that work out to be? Well, we got 5,000 milliamp hours. And so that's the battery we want. We're after a 5S battery that can handle 60 amps or more, 5,000 milliamp hours. Now, then the next issue has to do with the C rating of the battery. Now, the C rating of the battery has to do with how many amps it can deliver, but it's a factor. And the factor has to do with the number of amp hours that it's developing. So as we mentioned, this 5,000 milliamp hours is 5 amp hours. And if you multiply that by the C rating, then that will give us the current capacity of the battery. So as we have a look on the internet for batteries that are a 5S with 5,000 milliamp hours, the HRB batteries, if you look at those, it's just a low cost, halfway decent set of battery. They just simply come with, I think it's a 50C as I recall, and is 50 times 5, that's 250 amps that thing can handle. So we're talking about burst current of 100 amps at the worst, and continuous around about 60. So got lots of headroom for that particular one. If we were to look at the 6S solution, then the battery there, first off, we'd have a different calculation because it doesn't need 30 amps. It only needs half of the 40. So you're only going to need 20 amps of the battery times the same thing there. So you end up with a 4,000 milliamp battery. And if you get a 6S 4,000 milliamp battery with HRB, the lowest C rating they got is a 60C. So again, 240 amps. So huge of capacity there, and that'll be absolutely fine. Now, I might mention with that, I do like the idea of using batteries that have big C ratings. And the reason for that is that to say that the thing can handle 250 amps is to say it's got low resistance in the battery, and therefore with that amount of amps going through it, it doesn't create a lot of heat and destroy the battery. Well, that lower resistance is going to help you whether you're using 250 amps or whether you're using 60. Lower resistance, less wastage of power going into heat. The battery stays cooler. That helps other components in the engine compartment to stay cool, and it's just all good. So it's all fine and good to have that extra capacity there with your battery. And keep in mind that the C rating on the battery is what it can handle. What it's going to deliver is going to be determined by the motor and the ESC. Okay, if the motors demand it, the ESC is going to provide it, and it's going to draw it from the battery, whether the battery is going to blow up or not. It's going to come through there. So this is just a capacity that's safe to operate at. Okay, so we've got our motor selected, we've got the ESC, we've got the battery. Now how do we get it all connected together? That's an important thing as well. So we've got to think about connectors. Now you've got a variety of different ones that are available. These are the XT variety, and they're my preference. You've also got the IC or EC variety. IC if it's a spectrum set of 1, E-flight, or EC if it's a generic set of 1. They're supposed to be compatible. I have noted, however, I've got, like my P51 has got these connectors on it, and I find that sometimes when I'm plugging the EC into the IC that it doesn't seem to be as snug as what it ought to be, or it's super snug. You know, they can be a little bit different. And really with any brand of connector, that can be an issue. So it's probably a good idea as much as possible to stick to one particular brand of connector. As you think about the connectors, the one that's on the battery needs to be the safest one as far as not shorting on things, and that's going to be a female. Now the question is, what is a male and what is a female? Okay, so here we got a male and a female. Which one is which? Well, as far as the plastic bit, this one on this side is the one that is going inside the other, so you might think that that's the male, but as you look at the conductor inside, this is the one with the holes in it, and this is the one with the plugs that go inside. So in actual fact, it is the metal bit inside that's going to make the difference as to whether it's male or female. So the ones that got the holes in the conductor on the inside, that's the female. The one that has the solid plugs, or I guess not exactly solid, but the ones that go inside, that's the male. So they go together quite nicely. One thing I've noticed with this particular one, this is a XT90, is with this one, they've got a little bit of an air gap between the conductor and the plastic. That's all well and good, but when you're soldering it, you need to be careful not to heat it up too much, or the whole thing can bend and end up not lining up. So actually when I solder these things, and we'll talk about soldering later, and there's other videos that you'll find on YouTube that tell you about that, but when I solder that up, I make sure that I've got the other one plugged into it to make sure it's held in the proper position in case I get the thing a little bit too hot. I'm not sure if there's a benefit in that or not when it's actually operating in terms of staying cool, but the bottom line is that when you pick your connector, it's got to have the current capacity that you're going to be operating at. So at XT90, that's good for 90 amps, and we see that we're going to be operating continuous at 60. We've got the capability of going up to 75 continuous, or a burst thing of like 100 amps if we're looking at the ESC. You know, for this particular one, I think I'm comfortable with the XT90. XT60, you'd probably get away with it. I mean, 60 amps is the continuous thing that it can operate. So it's probably going to work, but, you know, better be safe than sorry. Of course, with the EC or ICs, you've got the EC3 and the EC5 and so forth. So EC3 would be a bit light on. That's what this one is. Probably go up to the EC5 if you're using those. And then, of course, there's other varieties of connectors as well. But make sure you use connectors that are rated properly, and make sure that they get soldered on really well. That'll be something that we look at later on our channel. But in the meantime, you'll find that there's a number of other videos put out by others on soldering techniques and things such as that that will help you to be able to do a good job. And I might mention with that I started out just using my standard everyday old soldering iron, and I found that I was melting the connectors, the plastic case for the connectors and stuff like that, and just wasn't working very well. And then I went out and bought a nice one that you know, has regulated heat and all that kind of thing, and it has a finer point on it, and that one just works absolutely beautiful. I mean, it's like night and day. So having the right gear is going to make a lot of difference, along with using the right techniques. Just one last thought on the batteries. Just because we come up with a particular number of cells and milliamp hour capacity and all that type of thing, that doesn't necessarily mean that it's going to work for your plane. Take for example this guy that we're working on here, you know, restoring it and all of that. As having been a nitro plane, getting the battery into that compartment where the fuel tank was a big issue. End up having to relieve it around the top to be able to get it in, and as such it just barely gets in there. And I've got another video that we're doing on this, but I've put in a bit of foam to hold the battery where it wants with the ESC underneath. But the physical size of the battery is going to be an important factor as well in what you select and how you go about doing it. For a lot of the foam planes, it's very common for me to have to modify the plane to fit the battery. And I found that not all manufacturers have the same size for the same specification of battery. Just thinking about the P51, when I got the E-Flight battery for it, or the Smart Spectrum battery, I guess it is. Get all their brands confused. But anyway, with the top dollar set of one, it's actually a little bit smaller physically and the higher C rating than, say, the ACE battery that was the equivalent with even a slightly slower C rating. The ACE battery is a little bit taller, and it was just tall enough to where using the battery tray that came with the plane, it wouldn't fit in. You know, so I had to make some modifications to make that work. Same thing with my Corsair. You know, having to make modifications to get the battery where I want it. So consider the physical size of the battery as well as you are making these decisions along the way. Well, that does it for today. I trust that this video has been helpful to you. As you have questions about things, feel free to jot them down in the comment section below. I read all of those, do my best to respond to them. And oftentimes they become the inspiration for the next video that I'm going to do. Of course, got a number of things in the works. We are continuing on with the restoration of this old plane, converting it to electric, and we're videoing all of that as we go along. Eventually that'll be online. We've got some more things to share about testing of electric motors and situations like that. So subscribe to the channel. You will find a lot of helpful things as we go along, and it's good to have them all at hand. So happy flying, and enjoy both your technical and hands-on work on the planes as well as getting out on the field and seeing how they go.